Hold on to your hats, folks. This is a good one. We're given a molecular formula, an IR, carbon-13, and proton NMR spec, and we're asked which is correct. Let's start off by looking at degree of unsaturation, also known as the index of hydrogen deficiency. That's equal to the number of pi bonds plus rings. For compounds A through D, they all have a degree of unsaturation of 4 because they have 3 pi bonds and 1 ring, and therefore aromatic rings have 4 degrees of unsaturation. Whereas E has an aromatic ring, that's 4, plus an additional ring, that's 5. So it's the odd one out and probably will be excluded. Now, there are many ways to calculate degree of unsaturation. This is kind of a easy way, although you may not think so because you've learned another. Degree of unsaturation is equal to 1 plus the number of carbons minus 1/2 the number of halogens plus hydrogens plus 1/2 the number of nitrogens. If we do the calculation, we get 1 plus 11 carbons, and as far as this portion goes, we have 1 halogen and 15 hydrogens. That's 16 divided by 2, and that gives us 8. So we have 4 degrees of unsaturation. We can officially exclude E from the answers. Now let's take a look at the IR. The IR provides absolutely no help. The absorption you see here just to the left of 3000 indicates sp2 carbon hydrogen bond stretch. That's from the hydrogens on the aromatic ring. They all have aromatic rings. No use. Here, just to the right of 3000, we have sp3 carbon hydrogen bond stretch. Well, that's all these carbon chains that you see over here, and so they all have those, so that's of no use. 1600, 1500 indicates carbon-carbon bond stretch in the aromatic rings. That's no use, and you don't need to worry about that. So we have to move on. Let's now look at the number of hydrogen environments. We see here that we have 7 hydrogen signals. So we need to have compounds that have 7 signals. Over here, remember there's no hydrogen here where carbon has 4 bonds to carbon. So we have 1, 2, 3. Remember that these and these here are symmetrical, so this environment here is identical to this, and this environment here is identical to this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This doesn't have a para, a 1-4 substitution, so it lacks symmetry. So if you count this, you'll get 10 hydrogen environments, and therefore you can exclude this. 1, 2, 3, 4, 5, 6, 7. So we now have 3 compounds left in the running. Now let's take a look at the number of carbon environments. So on the bottom here are the number of carbon environments. This is the off resonance, that's a non-split portion of the spectra. And if you go ahead and count, here's an example here, you'll find that there are 9 carbon environments, that here there are 9, and here there are 9. And so it turns out that, at least as far as the number of carbon signals goes, that is of no help to us. So I would next go to the proton NMR splitting, because I think that might provide some interesting information. Now, one of the things you can do is look for something that's very, very clear and helpful. This over here, okay, would be helpful if all of these aromatic rings that are left were not going to be substituted 1,4 or para, because this is called the doublet of doublets. And when you have a doublet of doublets, that means that you have a para-substituted benzene and that there is a difference in electron donating or removing power of those two groups. And we see here that they are all going to be para-substituted, and there is actually a way to get the right answer if you realize that if the chlorine is far away, it's not really going to have that same effect. You need to have something that's going to be removing electrons and donating electrons. And if you realize that, you can actually get to the answer quite quickly. But that may not be that reliable if you don't feel confident in doing that, and there's lots of ways to get the right answer, and you want to make sure you get the right answer. So let's take a look at another option. You should realize that except for the aromatic protons right over here and the doublet of doublets that come in around 7.25, that the most downfield proton signal is going to be due to the hydrogens that are going to be on the carbon next to the chlorine, because the chlorine is very electronegative. So let's take a look at this right over here. This right over here must be the hydrogens on the carbon bonded to the chlorine. And look, it's a singlet. Singlets are great because it means that when you have a singlet, you have no neighboring environments that cause splitting. And that's easy to pick up. Let's look over here, okay? If you look at these hydrogens here, they have hydrogens next door which cause splitting. So we can definitively exclude A. Now let's take a look over here. We can see that these hydrogens have neighboring hydrogens which are environmentally different. Therefore, the answer cannot be E because this would not be a singlet. Look over here. Here we've got hydrogens, and there's no neighboring hydrogens, and that's enough to use process of elimination to arrive at the answer. Now there's lots more information here. I just want to briefly explain that if you chose to, you could also use this portion up over here of the carbon-13. And the way this works is that whenever there's a CH2, you get a line going down. Wherever there's a CH3 or a CH, you get a line going up. And whenever there's a carbon, it's like this one over here or this one over here, which has no hydrogens, then there's no line at all. So that's an additional way of determining the correct answer. Like I said, it's a doozy. Correct answer, of course, is B.